Greetings, welcome to lecture number 25 on basic circuit theory. I am Razavi. Today we will continue to look at inductors and circuits using inductors. And we start out with a very simple circuit that consists of just one inductor and one resistor and see how it behaves. This is an example of what we call a source-free circuit or an undriven circuit, meaning a circuit that doesn't have an input, it has only an initial condition. And then we'll go over some more examples of these simple RL circuits to drive everything home. All right, but before we go there, let's just summarize what we learned last time. So we saw that we always start with this fundamental equation for inductors. And we observed that depending on what's going on with this equation, we can identify two important cases for inductors and, of course, similar cases for capacitors. In particular, we saw that if the voltage that is available for this inductor from the rest of the circuit is not infinity, less than infinity, then that means that this current jump cannot happen in zero time. So if the current is zero at 0 minus through the inductor, it has to be zero at 0 plus, right? Because they cannot jump. And that means that for that short amount of time, the inductor guarantees a zero current from here to here. And the only device that can do that is an open circuit. So the inductor reduces to an open circuit between 0 minus and 0 plus. And that's extremely helpful if you're trying to analyze the circuit around a switching event. For capacitors, on the other hand, we have to deal with current and whether the current available to the capacitor is infinite or not. If the current is not infinite, if the rest of the circuit cannot deliver infinite current, then if the initial voltage on the capacitor is 0 at 0 minus, it still has to be 0 at 0 plus. And that means that the capacitor acts as a short circuit, right? Because it wants to maintain that 0 volt difference, and the only device that can do that is a short circuit, is a piece of wire. All right, on the other extreme, if the current through that inductor is constant, so for example, all of the transients have died away, and we know that there's a constant current through this, then the voltage across the inductor has to be zero. It guarantees a 0 volt difference. And that would be equivalent to a short circuit. So the inductor reduces it to a short circuit after all of the transients have died away. For capacitors, it's the other way around. When the voltage on the capacitor has reached a constant value, the current through it is zero because it's equal to C dV over dt. If the current through a capacitor is zero, then the only device that guarantees that is an open circuit. And that would be for the capacitor. So the way we think about it is that in this row, when things have settled, everything is constant. The capacitor does look an open. See, there's an open circuit. These are two plates. There's nothing in between, so it looks like an open circuit, right? So it's an open. And the inductor does look like a short. This is the inductor, right? Over here, for this row, it looks like a short circuit. So that's how we remember it. Right? So that's a simple short circuit. So at time infinity, for example, if we are sure that things have settled, we can use these points to analyze the circuit. We talked about the energy in an inductor and series and parallel combinations and those things, and those are pretty straightforward. Okay, so today we'll begin to look at circuits consisting of resistors and inductors and experiencing some sort of transient behavior. So I'm going to start with a simple RL circuit. And we call this source-free or undriven response. Remember, we did this for capacitors also, for RC circuits, and the idea behind this is simply that we do not have any explicit inputs. All we have is an initial condition in the system, and we let the system go, and we want to see how the system reacts to this initial condition. Okay, so here's how we're going to do it. We start out with an inductor. We call it L1, and this inductor happens to have an initial current I0 through it. Okay, so somehow magically I created a current through an inductor equal to I0, some amount, 1 ampere, and I have it now available, right? And then this inductor is connected to a resistor R1. And we have only really two parameters here that we can find. One is this voltage here, call it V out. It's the same voltage for R and L because they're in parallel. And there's a current going through this loop, so we can find that current. We can call the current I out. And again, the direction of the current is up to us. So let's pick a direction. So let's say this current is I out, right? Not a big deal. You can call it this way, you can call it this way. It's entirely up to us. All right, so our objective is to find I out and V out as this inductor starts with this initial condition and the circuit evolves and does something. All right, okay. So, again, before we jump into the math, let's ask ourselves, what do we expect V out and I out to be at time infinity? Well, what we can think is this. This initial current through this inductor gives this inductor some energy, 1/2 I0 L1 I0 squared. Right? 1/2 L1 I0 squared is the energy stored in this inductor when we begin to look at the circuit. All right, but then that current through the inductor also flows through this resistor, right? You can see that it has nowhere else to go. It comes down, it goes this way, it goes up. As that current flows through the resistor, it creates thermal loss in the resistor, right? It creates heat. The resistor heats up. So the energy is lost from the system in the form of heat. It goes away. So as time goes by, whatever the transient might be, the current through the resistor is extracting energy from the system and dissipating it in the form of heat. So eventually what we expect is that all the energy inductor is lost to the resistor, and eventually there's no energy left in this entire circuit. And if there's no energy left, it means that the resistor cannot have any voltage on it or any current through it. So from this simple energy argument, we can say that the final values of I out and V out have to be 0. Okay, so we say our guess is that I out at infinity is 0 and V out at infinity is 0. Okay, because all the energy is lost. Now this is somewhat similar to when we had a capacitor charged and we connect to a resistor, right? The charge to the capacitor flowed through the resistor and eventually got dissipated. All the energy was lost and eventually there wasn't any current left or any voltage left. So this is similar. You can think of the inductor as being charged and now all of that energy is going away through the resistor. Okay, so we just want to analyze the circuit. We can find V out or I out first, whichever we want. Let's try to find I out first just to make it interesting. So find I out first. So we just want to write one equation containing I out and then solve that equation, right? Okay, so how do I write that? Well, I out is flowing through the inductor and through the resistor, so I can write an equation for inductor using its inductance value and its current, right, to find the voltage across it. So how much is the voltage across this inductor if a current of I out is flowing through it in this direction? So I'm interested in this voltage, which is actually the same as V out, right? This voltage is the same thing. How much is this voltage in terms of this current and this inductor? Now we have to remember from our discussions before that we have to be careful about the sign, right? So when we have the current going from high potential to low potential, is a positive sign here. When the current is going from low potential to high potential, there's a negative sign here. This is the case that we have in this situation. This I out is going this way from low potential to high potential. So this voltage here, is given by L1 di out over dt, but with a negative sign. All right, that's the voltage across the inductor. Okay, I have the voltage across the inductor. Can I find the current through the resistor? Sure, the current through the resistor is just that voltage divided by the resistor, or we already have the current, so we multiply that current by R1. So this is the voltage across the inductor, right? This voltage is the same as the voltage across the resistor. So let's equate that to R1 times the current through R1, which is I out, right? Or you can say the voltage across the inductor divided by the resistor gives us the current through the resistor, right? Either way. Okay, so this equation first finds the voltage across the inductor in terms of its current, then equates this voltage to the voltage across the resistor, which is given by Ohm's law. And it's a simple differential equation that we have. All right, to solve this differential equation, we need an initial condition. So we have this differential equation, and we need I out at time 0 plus. How much is I out at 0 plus? So again, you have to be very careful here. Okay, how much is I out at 0 minus? Well, we said that the current initially flowing through L1 is given by I0, but this current I0 has this direction, whereas I out has the opposite direction. So at 0 minus, I out is equal to minus I0. So let's write that out. So we say at t equals 0 minus, I out is equal to minus I0, because this is going this way, this is going this way, right? They have opposite directions. Okay, and then what happens at 0 plus? Well, we decided that the current through an inductor cannot jump provided that the voltage available for that inductor is not infinity. And there's nothing in the circuit that can give us infinite voltage, right? This resistor cannot give you infinite voltage because it would need infinite current, and we don't have infinite current. So there's no infinite voltage available, which means if the voltage cannot be infinity, the current cannot jump. So the current at a 0 plus is the same as the current at 0 minus. So I can say that this is the same at as if we had it at 0 minus. All right, so now we can solve this equation. It's pretty simple. It's very similar to what we did for RC circuits. But actually, it's even simpler if we go back to something that we learned a long time ago. If I have a differential equation of first order like this, where the other side is constant or a step function, either way, and the coefficient of y is 1, this coefficient is 1, then the time constant of the circuit is given by alpha, the factor that comes before the derivative with respect to time. All right? So then I can quickly predict the time constant of a circuit from this differential equation. I just have to write it in that form very carefully. So let's write it out. So we say what we have. We bring this to the other side and divide both sides by R1. So now we have L1 over R1 di out over dt plus I out equals 0. Is that okay? Take a moment to see how this happened, right? We brought this to the other side, divided by R1. This is what we got. Okay, so how much is the time constant of this first order system? The coefficient of the first derivative, because this coefficient is 1. So the time constant is just this value here, right? So we can say the time constant is L1 over R1. All right, we got that. Okay, I'm too lazy to solve this differential equation, So I'm just trying to rely on my previous knowledge of all these things. Why bother solving it again, right? Okay, so I have the time constant, I have the initial condition. How much is the final value of I out if we wait a long time? Well, I predicted that the final value will be 0 because the energy in the system disappears. Okay, so if that's the case, I can go back to my standard equation for the first order system's response. I can say that I out as a function of time is equal to I out at time infinity. How much is that? That's 0. Plus I out at time 0 plus. How much is that? That's minus I0. Minus I out at time infinity, 0. And then x of minus t over tau. And tau is L1 over R1. Does this take a u of t? Yes, because I out was, well, let's not apply u of t because we don't know what happened before time 0. We just write for t greater than 0. Okay. All right, so what does this plot look like? This plot looks like this. We have I out as a function of time. It's just, there's a minus here, minus I0 exponential, right? So it's minus I0, an exponential that approaches 0. And time constant is L1 over R1. So I out, the current that flows through the loop, according to the direction that I chose at the beginning, is negative initially, right? It's over here, and then goes towards 0. Going towards 0 makes sense because the energy in the system is disappearing. Why is it negative? Well, because the inductor has its own current going this way. So when we release the circuit, this is what's happening. This actual current, I0, comes down, goes this way, goes this way, goes this way. So if we have a current flowing from the bottom of R1 to the top of R1, then, and arriving here, that current is opposite of I out, right? Or you can look at it here, you can bring it over here, either way. So we see that the I out direction that we chose happens to be the opposite of the initial current through the inductor, and that's why that value comes out to be negative. Okay, alternatively, you could have said, no, I want I out to be going this way, and that would do it fine, then it would be positive, right? It just depends on the direction that we choose. All right, so that is the current that flows through the circuit. It's a simple exponential response. The time constant is given by inductance over resistance. Do not confuse that with RC for RC circuits, right? The resistance is in the denominator. So what we see is that, for example, if I increase the inductance, the circuit becomes slower, right? So if I change the color here, then it will be like this. If L1 increases, right? So a larger inductance in this case gives us a longer time constant. It takes longer for the circuit to respond. All right. Now, how about V out? Can I find V out from these results? Sure, there are different ways. Of course, the simplest would be to say that this voltage is just this current times this resistor. So let's write that here. We say V out is equal to R1 times I out. And we have an equation for I out, so that would be minus R1 I0 x of minus t over L1 over R1. And again, this is true for t greater than 0. Okay, that is the voltage. We can plot the voltage as well. It's very similar, right? The only difference is that there's a R1 here, otherwise similar to that. So this also says that at time is 0, 0 plus, this is 1, the voltage at the output is negative. Why is that? Why is the voltage that I measure from here to here is negative? Why is it negative? Well, this is because this inductor started with a current going in this direction, I0. The current comes down this way, it comes down and goes up here, right? So I0 is flowing like this. So we see that the current is going from the bottom of R1 to the top of R1. As a result, it generates a negative voltage across R1. So at time 0 plus, the voltage is negative, and then it approaches 0 as time goes by. Okay, so that's the response of this simple RL circuit. All right, so with that in mind, we can go ahead and look at some more examples to get comfortable with this idea. Let's see. Okay, so I just wanted to make a note before we go to another example to show you how we would create this initial condition. So when I started this problem, I said that this inductor has an initial current through it. And you might say, where did it come from? How did we do that, right? For a capacitor, it's easy. I have a capacitor. I put some positive charge here, some negative charge here, and that would be the initial condition. For an inductor, it's a little trickier, but here's how we do it. So to create the initial condition, we go back to a circuit that we studied last time. That's how we do it. We have a battery, we have a resistor, and we have an inductor. So here's RA, here's VA, and here's our inductor. Okay, you can see that if I let the circuit go for a long time, L1, then a current is created in this loop, which is given by VA over RA. Remember we calculated this last time? So this current is VA over RA. So using this topology, I can create the current that I need, and then I let the circuit go. So how do I go from here to here? This has its own resistor, right? So the purpose is to create an initial condition in this inductor and then let go of the circuit to make it look like this. All right, so here's how I would do it. I have my battery, VA. I have a resistor, RA. I have a switch here. And then I have these two components, L1 and R1. This switch is initially closed, initially on, like this, and then at time 0 it opens. So I claim that this circuit, that's what I want here. So before time 0, what's going on? Before time 0, we have a battery, VA, a resistor, RA, connected to the inductor and giving some current through the inductor. Do you remember last time we looked at this circuit and we looked at this circuit and we saw that the current through the inductor does not change even though you have a resistor here. So the current through the inductor is still given by this battery voltage divided by RA, some amount. So whatever I0 has to be, that's what we get from this circuit, right? VA over RA. So we say we create an I0 here. I0 is equal to VA over RA. Again, if you don't know where this comes from, go back to the last lecture where I explained this in detail. All right, now at time 0, we turn off the switch. We make it not conduct anymore. So this switch is open. Now what do we have? We have this inductor with a current of I0 and this resistor R1. So that's what we studied over here. All right, that's an example of how we create initial conditions in inductors for these types of studies. All right, let's go to another example here. So suppose I have a, let's see how did I do this? Okay, we have a battery. resistor R1, resistor R2, VB, and we have a switch here, and we have an inductor here, L1. And this switch turns on at time 0. It closes at time 0. All right? And we want to study the behavior of the circuit. All right, so take a moment to see what's going on and how we go about analyzing the circuit. All right, well, the first question is what happens before time 0? Before time 0, that switch is not conducting, so it's an open circuit here. We cannot have possibly any current through the inductor because it's connected to open circuit, right? So this current is 0, and we have this low circuit here, right? That circuit is sitting here. This battery creates a current through this loop. That's all we have. So, for example, let's say the quantity of interest to us is this voltage here. Okay? All right, so what we can say is that before time 0, V out is 0 because there's nothing in the inductor, right? There's no current, no variation, no time variation, anything. So that's what we can say. So we say t less than 0, V out is 0 because switch is off. So far so good? Okay. All right. So that means that the current through the inductor is also 0 before time 0. So we also say IL1 is 0 at t equals 0 minus. Right? Because nothing was connected to the inductor, so it has no current in it. Okay, so now we connect the switch. The switch begins to conduct. So what can we say? All right, well, our first reaction should be, maybe I should replace this part of the circuit by a Thevenin equivalent. So let's do that. So the Thevenin equivalent will have a voltage between these two terminals, which is equal to the voltage that you measure when this section is disconnected. Remember section A, section B. We disconnect section B and we measure this voltage. How much is that voltage? It's a voltage divider, right? So what we have here is R2 over R1 plus R2 times the VB. That's the Thevenin voltage provided by this section between these 2 points. How much is the Thevenin resistance? To find the Thevenin resistance, we set all independent sources to 0. This goes to 0. We sit between these 2 wires and measure the resistance of this section. So that would be what? It would be just R1 in parallel with R2. Because when you set a voltage source to 0, it becomes a short circuit. So it's a short circuit here. The R1 and R2 share both terminals. So our equivalent Thevenin resistance is given by this. Right? Okay, and then we have a switch that is conducting, so it's just a piece of wire, and then we have an inductor. So let's go to this inductor L1 and say this is the output of interest to us. I should mention that using a Thevenin equivalent is not the only way of solving the circuit, but it seems pretty convenient in the situation. All right, so I am interested in V out, but the initial condition that I have in the system is for the inductor, and that's in the form of a current, right? For capacitors, the initial condition is always for the voltage, and for inductors, the initial condition is always for the current. So we have decided that the initial current through the inductor is 0 at 0 minus. That's what we have to work with. So first we have to find the current through the inductor and through this loop, and then calculate the voltage from that current. And that's not that hard, right? So let's not worry about V out for the moment, and let's ask how much this current is. We call this current I out. Okay? All right. I can write I out by inspection without solving the circuit. Why? Because the first order system, if it's a first order system, we know how to write the equation for it, provided that we have the value at time infinity, the value at time 0 plus, and the time constant of the circuit, right? Okay, so how much is I out at time 0 plus? It has to be the same at time 0 minus, right? Because the inductor doesn't let its current change suddenly. So we can say I out at 0 plus is 0. Because it was also 0 at 0 minus. All right, how much is I out at time infinity? This is something that we have sort of seen in the past, so it shouldn't be difficult to predict. How much is the current flowing through this loop at time infinity? Well, it's similar to this case, right? So at time infinity, assuming that the current has become constant, the voltage across the inductor becomes 0. If the voltage across the inductor is 0, then the voltage across this resistor is this much, right? This voltage minus this voltage over this resistance gives us the current. So we can say that I out at time infinity is this voltage, given by its value, minus 0 divided by this resistance, just like here. So we can say that that's VB R2 over R1 plus R2 divided by R1 in parallel with R2. Right, this voltage divided by that resistance, because this side is 0. Now that's interesting, and in fact something looks pretty suspicious here, because R1 in parallel with R2 would be R1, R2, and then R1 plus R2, so those cancel each other, and it just ends up being VB divided by R1. So the current through the inductor at time infinity is VB over R1. Does it make sense? Sure, let's go back here. At time infinity, remember this is a switch, it's conducting, right? At time infinity, this wants to force a 0 volt difference between these two because it's a short circuit, because it has a current that is constant with time, right? So L di over dt is 0. This voltage is 0. This voltage is 0. How much is this current? This current is this voltage minus this voltage, VB over R1. So we have a current of VB over R1 going this way at time infinity, right? VB over R1. That current comes in here. Where does it go? Can it go through this? No, because this inductor has a 0 volt difference, which means this resistor has 0 volt difference, which means the current through R2 is 0. So all the current from this guy flows this way, just the way we decided this before. So it's not surprising that I out, meaning the current to this inductor at time infinity, is VB over R1. Okay, so I have found these two quantities. I just need to find the time constant of the circuit. Then I can write out my equation. How do I find the time constant? Well, the situation is similar to what we did for capacitors. We set all independent sources to 0, and we take the inductor out and see what kind of resistance it sees. Can we do that in our head? Here's the circuit. Take this out. When you take this out, what happens? It's replaced by a short circuit because they're a voltage source, right? It's an independent voltage source. Replace this by a short circuit. So it's a wire. Take the inductor out and sit here. What do we see? We just see this resistor here, right? So the resistance, equivalent resistance seen by L1 is R1 in parallel with R2. Could have seen that here too. If you set this to 0, these two go in parallel, and L1 sees both of them in parallel. So we can say that tau is equal to L1 divided by the resistance that it sees, and that resistance is R1 in parallel with R2. So now we can go ahead and find I out as a function of time. So I out is I out at time infinity. How much is that? It's this quantity. So this quantity. So it's VB over R1. And then at time 0, it's 0. At time 0 plus. So we just write that as 1 minus x of minus t over tau. And that's all we need, because at time 0 you can see that this is 1, so we get 0 here. That's as expected. At time infinity, this is 0, we get that, and that's also to be expected. So that's our equation for the current through the inductor as a function of time after the switch begins to conduct. And we can put a u of t here because the current through the inductor before time 0 is 0. All right, how do we compute V out? Well, V out is just L1 di out over dt. So say V out is L1 di out over dt. So we take the derivative of this, multiply by u of t times L1. Then we take the derivative of u, becomes a delta, an impulse, multiplied by this times L1, right? Then what happens? Do we have an impulse or not? No, we don't have an impulse, because if you look at the weight of that impulse, the area associated with that impulse is 0. So I'll leave that as an exercise for you. We've done this in the past, so you can go through it and see. You can see that when you take the derivative of this, it's delta of t, but it's still multiplied by this. And how much is this at time 0? It's 0. So the area associated with that impulse is 0, so that impulse does not come into the picture as far as V out is concerned. So V out will be only the derivative of this times u of t times L1. So I'll just write that part here. So it will be L1 VB over R1 times the derivative of this, which is minus 1 over tau times minus, so 1 over tau, and then exp of minus t over tau. Okay, and V out also takes u of t, because we're multiplying the derivative of this by u of t. All right, so the other part, the derivative of this times this, so say something like this times delta of t, this part is 0. So that part goes away. There is no impulse in the voltage that we measure at the output. All right, okay, so that's the basic behavior of the circuit. What does the voltage look like as a function of time? It's just a decaying exponential. So it starts out with an initial value, which is which would be this voltage here, and then initially this inductor has no current, right? So this voltage is equal to this voltage, and as time goes by, this voltage goes towards 0 because the inductor acts as a short circuit at time infinity. So the voltage as a function of time will look like this. And this value is this guy here. So I don't have room on this side. I will write it here, VB R2 over R1 plus R2. Okay, so before leaving this example, why is it that the initial value of V out is this much? So this is because at time 0 plus, the current to the inductor is still 0. If this current is 0, this current is 0. If this current is 0, this voltage drop is 0. If this voltage drop is 0, this voltage is equal to this voltage. So V out is that much. As time goes by, the voltage across the inductor drops, so it drops towards 0. All right, so that was an interesting example. You can see that compared to the simple case, it's a little more complicated because we have to go through these steps, but we can always rely on our general equation for a first order system, and that's the beauty of these equations. Okay, let's go and look at a couple of more examples of these circuits. So again, we're just looking at very simple structures and trying to get comfortable with these ideas. All right, so the next example we'll look at is this here. So if I have a capacitor and I place some charge on it, Q, and I let it sit, what happens? Well, in principle, it just keeps this charge and voltage forever, right? So that's great. The capacitor is not connected to anything else. We can say the capacitor is connected to an open circuit, right? And it keeps that voltage on it, that charge on it forever. Now, for an inductor that has an initial condition, what can I do to make sure that that initial condition stays in the inductor forever? It has to be dual of this, right? There's a capacitor connected to an open circuit, right? Capacitor connected to an open circuit. If you have an inductor and it has an initial condition of I0, obviously this doesn't work, right? Because this I0 has to flow through something. We cannot leave it open. But if we connect it to a short circuit, then this I0 can circulate indefinitely, right? So the inductor maintains its initial condition and the current just flows forever. Of course, this is an idealized situation because we know in practice these wires and so forth have some resistance in them, right? Some finite resistance. So even if I use this piece of wire as my short circuit, it has some resistance. So the current flows through that resistance and gradually turns into heat. The energy turns into heat. So eventually the current disappears. But in principle, if we want to keep the current through an inductor forever, we have to short the inductor between its terminals. This is the dual situation of what we have for a capacitor. Okay, so we create a circulating circuit, right? The current circulates around this loop. All right, so that's good to remember because we will see that the situation becomes more interesting as we go along. All right, so let's look at another example where we have something like this, but a little more complex. So here we will go and do this. I have an inductor and there's a current of I0. I have a switch that opens, stops conducting at t equals 0, and then I have a resistor R1. And I want to plot this voltage as a function of time. So this circuit becomes very interesting. You can see that initially the switch is conducting before time 0. So maybe I'll draw it for before time 0 just so that we can visualize what's going on here. The switch is a short circuit, right? And the inductor looks like this, R1. And then there's a current of I0 here. And that's our inductor L1. So we have a current of I0 through this inductor. You can recognize this as our circulating loop, right? That's perfectly fine. We can have that current go around that loop. Does any of this current go through R1? No, because if R1 is shunted by a short circuit, that short circuit guarantees a 0 volt difference between these two terminals, so the resistor has no current in it. So the entire I0 must flow through this little loop here, just like before. That's what happens in this circuit. Now what happens when the switch turns off? Well, a lot of interesting things happen. And I'll keep you in suspense until next time. I will see you.